Hello, everyone, and welcome to the final lesson in Chapter 11. So far, what we've learned in Chapter 11 are the chi-squared tests, and specifically the goodness of fit test and the test for homogeneity. What we're going to learn about today is the third and final chi-squared test for the curriculum, and that is the chi-squared test for independence. So to help answer this question, we're gonna look at or to help answer this topic, we're gonna look at this question: Are gender and favorite color independent? So is there an association between gender and preference of English or math class? Below is data for a random sample of senior students. Do we have convincing evidence that gender and favorite class are associated? So before, what we've had for the goodness of fit test is we had one single sample and one variable, and that was M&Ms, one sample of M&Ms, and the color distribution was the variable. For the homogeneity, we had 2+ samples, so we had the Haribo gummy bear sample, and then we also had the other gummy bear sample, and then we were just looking again at one variable, and that was color distribution. Well, now what if we want to see if within one sample, uh, is there an association between the variables in that sample? So let's go back to chapter 5 now, and we had to describe what does it mean when two events are independent. Well, if some of you are recalling this, there was a formula that we kind of used to work our way through this, and that was that if the probability of event A occurring was equal to the probability of event A occurring given B occurred, which would also mean in terms that the probability of event A given B did not occur. Let's see if I can get that to right. B did not occur. If all three of these were equivalent, then we would say, that A and B are independent. And then this is what we use to show that, when the events are independent, well, then the probability of A and B is equal to the probability of A times B, whereas it usually would be, that the probability of A given B times B. This is usually what you'd have to use right here, but if it's independent, you could use this right here. And that's just a little review, because we have the AP exam coming up in about a month or so, so just got to make sure that you're always reviewing there. So this would be the formula version of this situation, but if we wanted to maybe put it in words, what we could say is that knowing if an event occurs does not change the probability of another event occurring. So in words, knowing if an event occurs does not change the probability, shorten that, of another event occurring. Okay, so this is what we're going to have to think about as we answer this question. So the overarching question of this lesson right here is: do we have convincing evidence that gender and favorite color are associated? Now, if two things are associated with each other, that's like the same thing as saying that they affect each other, right? They have an effect on each other. So if two things are associated, then what we're really saying is that they are dependent. Whereas if they are not associated, well, if two things are not associated, well, then they are independent. So you just have to remember this, because you'll see these questions with the word association, and you'll see these questions with the word independent, and you have to just go back and try to think, well, what would it mean if A and B are associated? Okay, so now let's go ahead and take a look at this fake data that we have right here. So we went out and we surveyed 114 total people, and we broke it down into gender and their favorite subject. gender and their favorite subject. So for the gender, we found out there were 65 females and that there were 49 males. We found out that of the entire survey, 50 preferred math and 64 preferred English. And then we have the males that preferred English, we have the males that preferred math, the females that preferred English, the females that preferred math, all right there. So we have the observed data. Now we want to calculate the expected. And this is done the exact same way that we just learned about in the previous lesson. And that would be start off by writing the totals in, because the totals are going to remain the exact same. So we still have 65 females. We still have 49 males. We still have 64 people who preferred English and 50 who preferred math, which totals up to 114. So now how do we calculate the expected values? Well, what would you expect the number of females to be that preferred English if the events were independent, or because we're testing to see is there an association. So what we're assuming at the beginning is that there is no association, which would mean that we're assuming at the beginning that they're independent. So let's try and calculate this as if the two are inherently independent or proportionally equal to start. So how do we do that? Well, it's the row total. So there's 65 females times the column total. There's 64 people that prefer English divided by the sample size, which is 114. So that gives us 36.49. What I want you to do now is to pause the video here and fill out the remaining 3 boxes. Okay, everyone. So now we've filled out the expected values that we should have if the 2 variables were independent. So this is our observed value. We observed that 22 females preferred math, but we expected about 28.51 to prefer math. We found that 28 males preferred math, but we only expected 21.49 males to prefer math. So using this information, the observed and the expected, what we're going to do is we are going to perform a chi-squared test for independence. So taking a look down here at question 3, I'm going to start off by stating the hypotheses, and then I'm going to send you off on your own to complete the rest, because it runs the exact same as the previous 2 procedures that we learned. So for the hypotheses, you start off by writing your ho and your ha. So your ho and your ha, and let's maybe put this in a different color. Your ho is what do you assume? So what are we initially assuming? Well, what we're testing is, does the data provide significant evidence that there is an association between gender? Whoops, I don't know what just happened there. Between gender. Weird. There we go. There's an association between gender, preference of English or math class. So this right here, this last sentence, it's always going to be our alternative hypothesis. It's what we're testing. So our null hypothesis is the opposite of that. So we're going to assume for right now that there is not an association. So there is no association between gender and favorite class. Our alternative is there is an association between gender and favorite class. The significance level is given to us right here. It says A is equal to 0.05. It should be alpha is equal to 0.05, and that is what we're going to be testing it against. Okay, I want you to pause the video here, and then I want you to complete this entire significance test. All right, everyone, so here is the final answer for this significance test. Going through the plan, do we conclude? First, we have the name of the procedure is the chi-square test for independence. And then the two conditions we need to check are 1 is random, and 2 that we have we were expecting a large enough number of counts. And so we check large counts. We say first that the lowest expected value is 21.49. That's that male math total right up there at the top, and that's greater than or equal to 5. So if the lowest is greater than 5, then we can say that all of the remaining expected counts will be greater than 5. Now we need to do the actual work for this. So we need to figure out, well, what is our test statistic that we can then find the p-value for. So chi-square test statistic, well, the specific formula for this will always be the same, and that's going to be the sum of all observed values minus expected squared over expected. And so this would be just piece by piece, 43, which is this female English, minus what we expect, which is over here, 36.49, squared divided by 36.49, plus, and then you're going to go through all of these until you get to the last one, which is 28, or just the way that I did it has it so that it's our last one is not 28. Our last one, by the way that I wrote it, is 22 minus 28.51 divided by 28.51, and then obviously that square up there. So you end up with a chi-square test statistic of 6.16. So if I shade in the picture right here, this red area here is what our p-value is. And to find the p-value, well, let's go on to our formula sheet. And we're going to say, okay, so we have a chi-square test statistic of 6.16. And we have a degrees of freedom, which is equal to the row minus 1, the number of rows that we have, times the number of columns that we have, minus 1. And so, well, we have 2 rows, so we have 1 times 1. And so we end up with the degrees of freedom of 1. So going on to our degrees of freedom of 1 right here, let's go across until we find that 6.16. That's 6.1. Oh, might have actually passed it right there. So that's 6.16. Well, we know it's going to be greater than here, but it will be less than here. So we lie somewhere in between 2% and 1%. So you could estimate it at about 0.0115 if you wanted to just use an estimate. But you might be asking, well, Mr. Leon, how did you get this 0.013 right here? Well, as always, there is a way to use your calculator to solve these chi-squared tests. And so let's pull out our calculator now and work through this together. Okay. So I have my calculator here. First thing I'm going to do is insert a list of my observed in list 1 and my expected values into list 2. So stat, and then I click edit, and I've already gone ahead and done this. So I have 43, 21, 22, and 28. And then my list 2, notice I am matching up the expected values and the observed together. So 43 is what I expected. So in the second list, in list 2, I need to have 36.49 next to it. 21 is what I observed down here. 21 is what I observed right there. And so I need to have 27.51 next to it. Then we go to 22. We need to have 28.51 next to it. And finally, this 28 right here needs to have the 21.49 next to it. And now we can just use the calculator function. So let's exit out of this. I'm gonna quit it here. Back to the main screen. now what we do is we click Stat, we go over to the Tests, and we're going to scroll down until we find something that says chi-squared on it. Okay, so we have, oh, I went too far. So we have up here, whoops, in the wrong spot. We have up here, we have C and D, both say chi-square tests. And so I'll start off on C and just show you what this is. With this, we won't end up ever using this C. And so what C does is it allows us to enter in some matrices and find the chi-square test that way. But instead of doing that, let's just use what we've been learning all year. And let's use just the lists. And so in order to use the list, you're going to use this chi-squared goodness of fit test button. And you're going to use this button regardless of the test. So right now we're doing a chi-square test for independence. Yesterday we learned about a chi-squared test for homogeneity. It doesn't matter. You're always going to use this function here regardless of what type of chi-square test, because in the end, the do sections all look the exact same. So chi-square goodness of fit, I click enter. I have my observed values in list 1. I have my expected in list 2. My degrees of freedom is 1. I had to enter that myself. And I go down to calculate, and voila. So this will actually save you a lot of time for figuring out what the chi-square test statistic is. So 6.16 matches my 6.16. And this p-value here of 0.013 is where I got this p-value right here. Okay. One more thing actually that I want to show you on this is the last thing where people are kind of confused on is this CNTRB right here. What this is telling you is for each actual, or this is each observed minus expected squared over expected. So for the female English version of that, the first numbers that we entered in, the 43 and the 36.49, they were 1.1 away from each other. And as you scroll over, it's giving you just every single box is how far they were from each other. And so you could use this right here to tell the readers or the graders, you know, which one was the farthest from what we expected. And you could see this last number here is the largest, not by a lot, but it's the largest. And so you could say, well, therefore the male math was the farthest away from what we expected it to be. Okay, so that's what that number there is. And last, we're just going to conclude that because our p-value is less than what our alpha level is of 0.05, we reject Ho. We have convincing evidence that there is an association between gender and favorite class. Okay, so for the learning targets, you can go ahead and pause it here and copy these down. Okay, so the first learning target is just the chi-square test for independence. And I mean, really the only difference between all the tests are how you write the hypotheses and what the specific name is. And so for these hypotheses, you're going to start off with the assumption that the two variables are independent. And so you're going to say there is not an association between the two. And really what this is saying is that they are independent. And what we're testing is there an association? So there is an association between them, and that's that they are not independent. So they're dependent is what that's really saying. Learning target 2. Which chi-square test should I use? Well, we've learned 3. We've learned goodness of fit, homogeneity, independence. So when do you use which? Well, it really just depends on the question. And specifically, it depends on how many samples did the experimenter, or how many samples did the surveyor take, and how many variables are we comparing. So for chi-square goodness of fit, well, you'll run a chi-square goodness of fit. You'll really just write down a chi-square goodness of fit when you have exactly one sample that was taken and one variable that you're looking at. And we could think about our example here, which would be the M&Ms. The M&Ms there. For chi-square test for homogeneity, well, this could be 2 samples or more. So 2 samples plus. And you have just, again, one variable. So the example that we did with this would have been the gummy bears, gummy bear brands. Right, so we had Haribo, we had here, and we could have also grabbed in Black Forest, and we could have grabbed in just maybe Target brand gummy bears, and we could have had 4 samples of gummy bears and just tested to see, are the color distributions all the same for each. And then the last would be chi-square test for independence, and well, this would be, let's think about what we have in this previous lesson. We took one sample of 114 seniors, or 114 students. Oh no, yep, seniors, a random sample of senior students. So one single sample. And how many variables do we have? Well, we have one variable here with favorite subject and another variable here with gender. So when you'll write chi-square test for independence, it will be when you have one sample and 2 variables. And that's when it'll be the chi-squared test for independence. And this is what we did today. So now what I'd like you to do is, for each of the following situations, decide which type of chi-squared test would be the most appropriate, and then explain why that would be. So I'd like for you to pause the video here and work through this, check your understanding. Okay, so our first check your understanding question: shopping at secondhand stores is becoming more popular and has even attracted the attention of business schools. A study of customers' attitude toward the secondhand stores interviewed separate random samples of shoppers at 2 secondhand stores of the same chain in different cities. The two-way table shows the breakdown of responses by gender. So in this case, we have a chi-squared test for homogeneity that we would be running, because we have 2 separate samples. So 2 samples, 2 plus samples, like what our learning target says, and we just have one variable, and that variable would be gender. And each one of these stores are a separate random sample right there. The General Social Survey asked a random sample of adults their opinion about whether astrology is very specific, sort of specific, or not at all scientific. Excuse me, scientific is what I meant to be saying for all those. Here is a 2-way table of counts for people in the sample who had 3 levels of higher education. So if we were running a significance test for this, it would be a chi-square test for independence, and that is because we took only a single random sample, and we are then going to look to see if the 2 variables have any sort of association, and the 2 variables would be degree and opinion. Degree and opinion. And last, casinos are required to verify that their games operate as advertised. American roulette wheels have 38 slots, 18 red, 18 black, and 2 green. In one casino, managers record data from a random sample of 200 spins of one of their American roulette wheels. The table displays the results. So, just from the question, I'm reading that there's one sample and that there's going to be one variable, and that will be the results. So this would be a chi-squared goodness of fit. And so that's going to be the reason is that we had one sample of 200 spins, and we are looking at one variable, and that is the results of this variable. So what color did each of the spins come out to be?